Greetings to one and all. I am Ashish Laddha, PhD scholar, MNIT Jaipur, Rajasthan, India. I am presenting the paper entitled Power Optimization in DC Microgrid with Monetary Perspective on behalf of Dr. Vijayakumar Krishnasamy, Nandha Kumar Kandasamy, and Satyanarayana Neeli under Special Session 6 of the ISGT-Asia 2022. This is the presentation flow: introduction and motivation, system description, program formulation, applied methodology, input parameters, simulation results, conclusion, and references. Introduction and motivation. Distributed generation involves power generation at places nearby or at the same location of customers' power demand through conventional or renewable power sources. Renewable resources in the form of distributed energy resources, DERs, improve power quality, energy management, and power sharing. By hybridizing the DERs, we usually assure that the generation is more flexible and reliable. Our system can be seen as more resilient. Intermittent behavior of the DERs necessitates certain energy storage provision like battery bank so that customers' power demand could be uh, met at any instant of time. Microgrid, as a miniaturized structure of the conventional grid, comprises of the distributed energy resources, energy storing devices, smart devices, and loads. Now, conventionally, microgrid is utilized with the AC supply, but actually, most of the renewable distributed energy sources and energy storing devices outcome their power in the DC form. Then, various loads in different walks of the human life are also uh, available in the DC form, and the DC operated energy meters enable the measurement of energy uses of various devices of a DC power network in the DC form itself. So, the DC microgrid is usually preferred over the AC microgrid. Additionally, the DC microgrid is free from the problematic issues like skin effect, proximity effect, synchronization, reactive power, which are usually associated with the conventional AC powered microgrid. Perspectives like control, power quality, protection, and efficacy improvement in the context of the DC microgrid have been widely discussed in literature. Apart from these perspectives, the monetary aspect or perspective of the DC microgrid is also significant to evaluate its real-time implementation feasibility. That's why this study presents a comparative analysis of the equated price per annum of the hybrid DERs incorporated in the studied DC microgrid. System description. The figure 1 shows the studied DC microgrid. Here, biomass gasifier, battery bank, and solar PV, as are visible on the left hand side, present the first hybrid DER, whereas fuel cell, battery bank, and solar PV formulate the second hybrid DER. And then we have front end converters, mainly DC to DC, and one AC to DC. Then controller, MMU means metering and monitoring unit, DC buses, 380 and 48 volts, back-end converters which are DC to DC, and different type of DC loads. The main objective of this study is to minimize the equated price per annum P of the hybrid DERs as per equation 1. This P is equal to PR net running price plus PI installation price plus PM microgrid price plus PU utility price. The one is subjected to equality constraints. There are two equality constraints, one for each hybrid DER. The first one tells that the customer power demand CPD at every instant of time should be able to met by the available generation in the DC microgrid of figure 1. The negative sign before PWV means vending power, indicates that the extra power, extra generation available in the microgrid could be sold to the utility grid. Similarly, the second equality constraint corresponds to the second hybrid DER. Additionally, we have an inequality constraint uh, uh, expression as shown in the 2. This conveys that the power outcomes of the biomass gasifier photovoltaic fuel cell should be greater than 0 and lesser than their installed capacities, and in the case of solar should be lesser than the hourly peak generation of the solar PV. Here H and C denote hour and customers respectively, and the negative sign before the installed capacity of battery bank on the left hand side indicate the indicates the charging operation of the battery bank, and whereas the positive limit of battery bank installed capacity of battery bank indicate its discharging operation capacity. And additionally, all these powers installed capacities must be positive. We are utilizing social spider optimization SSPO meta heuristic optimizer, which is a community based technique and works on the biological behavior of the social spiders. What features are unique about this? The gender consideration of the spiders, superior location allocation mechanism, fine function in God provision to keep constraints within the desired limits, and it has successfully been tested on 8 thoroughly studied CEC 2006 test suite benchmarking, as well as 3 engineering optimization problems. Figure 2 depicts the working of the social spider optimization. Input parameters, figure 3 shows the hourly customer's power demand on arbitrary summer and winter days. Here PDS is the customer's power demand during summer, whereas PDW is the customer's power demand during the winter season. Table first presents the running prices of various distributed energy resources. Here dashes in front of a particular DERs convey that that particular DER is not applicable to that particular hybrid DER. Table second is about installation prices of the DERs. Table third is price and lifespan of the DC microgrid equipment named switching device, transformer, controller, and cables. Table fourth represents installed capacity of the distributed energy resources. Table fifth presents the vending prices for different scenarios of the customer's power demand, namely normal, off-peak, peak, as detailed in table. Simulation results which have been obtained through the MATLAB editor environment. Figure 4 presents the optimized power operation for the first and second hybrid DERs. Here, the dimension indices on the x-axis tell that how the biomass gasifier and other distributed energy resources contribute in the optimized power outcomes. Continuing with the results, equated price per annum. Here, figure 5 and figure 6 show the equated prices per annum for the first and second hybrid DER. The figure 5 is for the first hybrid DER, figure 6 is for second hybrid DER. It is observable from these figures that the social spider optimization provides the least value of equated prices per annum in each case. Table 6 presents the comparison of the equated prices per annum for both the hybrid DERs correspond to the social spider optimization SSPO and particle sum optimization PSO. So it is observable that social spider optimization provides the minimum equated price per annum than the particle swarm optimization. Conclusion: this comparative analysis revealed that the second hybrid DER provides makes the DC microgrid more feasible from the implementation point of view, and the SSPO provides the better result than PSO, and the vending prices convey that purchasing of power during the off-peak operational hours of a day is profitable to the customers. These are the references. Thank you.